Okay, maybe we'll get started now. Thank you everyone for coming to this first webinar of the new year. Today we have Mike Miniter presenting his work on porting the OPTCLIM optimization system to ARCHER2. Now, if you have any questions during the talk, feel free to use the chat and I'll relay them onto Mike, or alternatively, you can hold on to them until the end and we'll have a short question and answer session then as well. Thank you. Okay, so take it away, Mike.
Well, hello everyone, and thank you very much for being here. So I work as the modelling officer in the School of Geosciences at the Edinburgh University. And in that role, I've been working with Simon Tett and Andrew Scherer on this project, and until his departure back to Germany, Magnus Hagdorn. As you'll hear, our co-investigators, Cora, Dan, and Maria, brought expertise in different aspects of the project. So we're focusing on how to optimize Earth system models. In our case, the word optimization is about achieving a better representation of reality, not as is usual in the ARCHER2 series, making a single code run more cheaply. Participants in the webinar may be from other domains, so I'll give a short introduction to Earth system models, which is our focus. We ported software we had previously used on the Edinburgh cluster, EDI. I'll explain what it does, how we have a software framework that orchestrates runs of a model, and why. Then I'll talk about how we made the software OPTCLIM run on ARCHER2 with 3 models that it hadn't previously linked to, and outline work with a related development called particle filtering for one of those models. This is an ECSE project for porting software to Archer. So the goal is to provide software that others can use. I'll give an orientation for those who might wish to do so at the end. And the goal of using this software is that it leads to more accurate models that can themselves benefit research. So a quick look at different kinds of Earth system models. Above the red line shows typical components of a climate model. And below the red line shows that an Earth system model is basically a climate model with a full carbon cycle. General circulation modeling considers the ocean and atmosphere with the same software kernel. On ARCHER2, we linked our OPTCLIM software to the 3 models noted there, the MIT general circulation model, and in particular to a use of it called ECHO for estimating the circulation and climates of the ocean. Dan Jones guided us in that. And then CESM2 is the US community Earth system model, and Maria van Martin was our co-investigator and guide there. The UKESM is the UK equivalent of an Earth system model from UK Science, and here we relied on NCAS, the National Centre for Atmospheric Science, who support the academic community in modelling with this. And we also relied on our own experience with UKESM, which got stretched. So the rationale for modelling includes those points to the left to do with building community knowledge, doing experiments like what would happen if carbon dioxide concentrations in the atmosphere were suddenly reduced. And also to do with understanding observation and projecting the future. So a model receives an initial state and calculates new states every model time step, writing these out at a chosen periodicity. This shows a tiny fraction of the kind of data in that state. And an example is here the surface temperature. There's also ancillary data, which is the inputs to the calculations, such as solar intensities and greenhouse gas concentrations. And then lots of parameter values are used in processes that's impractical to resolve from first principle, such as we can't model every raindrop. And so cloud processes in particular are parameterized, and there's and these are the focus of some of our work, as you'll see. Typical research use is shown on the left to copy a reference model, one that already exists, so that it's very rare that a researcher would begin with a complete empty, having to make a definition from scratch. But they tend to begin with a reference model, make some changes, then run a simulation, take a look at the results, and then do a comparison with the reference model's results and with the historical record in order to explore some kind of scientific hypothesis. So I want to focus now on the particular software that we ported and put onto Archer. This is software we'd previously used on our Edinburgh cluster, EDI, and OPTCLIM and particle filtering are the two flavors of this software. And I'll explain why we developed these. It's all to do with responding to uncertainties in models. So these arise from having imperfect information as inputs to the model and having imperfect representation of physical processes within the model. And we seek to respond in two ways. As you've seen already, many processes in the model are parameterized. And the goal with OPTCLIM is to find parameter values that best fit observation. On the right-hand side, you see the role of cloud in changing the short-wave and long-wave radiation. And that's, that radiation is something which can be measured from satellites. And so our first use of OPTCLIM was to look at the observations of long-wave and short-wave radiation as global averages and tune model parameters in order to fit those observations. Then the second aspect, led by Andrew Shearer, who's I noticed was on the call, is to do with particle filtering. And this is motivated by the fact that systematic change can happen. So that what's being shown in the image on the right is the deviation in ocean temperatures, which happens with an El Nino, so that there's warming of parts of the ocean with the El Nino effect. And models will tend not to follow a historical time series unless you run them very, very often and try to have a diversity of parameters and a diversity of inputs, so that tracking a historical timeline like an El Nino is very difficult. So that a technique called particle filtering, based on an ensemble of simulations, where each member of that ensemble is termed a particle, is the approach that Andrew's been looking at. Now, one of the things that's important that opens up these methods and also challenges them is to ask what's different about this kind of model. So the first thing is that they're very expensive to run and run for a long time on many cores on the most expensive computers. So that we need to minimize the number of runs. And secondly, these are deterministic models, so there's potential for algorithmic approaches. So in the way in which we explore to get best parameter values and explore to follow a timeline. They have these things in mind, and that opens the door to us for the methods that we're using. So with OPTCLIM, this is the sort of schematic of what happens, so that we begin by defining values, and the OPTCLIM software sort of defining starting points for these parameter values. The OPTCLIM software then determines the values to be used in several model runs, and these runs then generate data from which we can calculate simulated observations and compare them against against observation. So that simulated observations are compared against the in the previous example I gave was the satellite observations, and then with those deviations and the parameter values, we can run the optimization algorithm and generate more values of parameters, and then run the models again. And when we run the models, we're cloning a reference base model, then amending the parameters as defined by the OPTCLIM algorithm, and then running the simulation. Now, so this is the loop that we go around until either the simulated observations are fairly close to the actual observations, or we've done enough runs that we feel we're not going to make further progress and have defined a boundary to the number of runs that we make. An example of that from a system test is here, where we've got just two parameters, and these are shown in the lower graph as being normalized to between 0 and 1. So we began with these values and then perturbed them in turn, and explored the cost or the quality of fit, excuse me, the quality of fit to the observations, and can see that that in time came down. So that was just a simple system test that we did on Archer to demonstrate that the OPTCLIM software architecture was behaving itself. Now we'll look at how this schematic on the left gets actually expressed in software and data. Excuse me. So working clockwise, we begin with some kind of configuration of the study. That's then read in by the OPTCLIM core. That determines how many runs it wishes to make and the parameter sets for each of those runs. Each of those runs is then cloned from a base run. Here's just a copy of that. The parameters for each of those clones are then applied, and the model then executes. On completion of the model, then we calculate simulated observations for each of the models that's run. And then when all of those simulated observations have been calculated, we then have a further step which just re-invokes the OPTCLIM core, which gathers the results to date, and then sets a new set of runs with a new set of parameters. And so around the loop we go. And one of the factors that helps us to keep this synchronized is that we have what we call interface directories. Well, firstly, a study will usually will have a unique name. So in this case, we've got a study called ZD, and the runs generated by OPTCLIM will be numbered ZD1 and upwards. So that ZD is a unique identifier for that particular study. And within ZD 001, we hold the data which are generated by OPTCLIM and needed by the model, and the converse, the data that are generated by the model and the simulated observation calculations, and are needed by the OPTCLIM core to run the optimizer itself. The OPTCLIM core then gathers the simulated observations and parameter values from all the completed runs and generates new parameter sets. And it does it using an optimization software called DFOLS, which was generated by Cora Curtis and colleagues at Oxford. And that's the link for it. I realized that I didn't have that link in the project report, so I apologize. So the optimizer generates new parameter sets, and each set gets cloned, modified for the parameters, and then run. The way in which the configuration file contains the definition of the parameters to be used, the script that generates the simulated observations, the values of the simulated observations, and any parameters associated with the optimizer itself, so that DFOLS has a lot of options and it defines what those options are for us. The way in which this is expressed in the batch workflow, and we're still looking at what happened on Eddy, and in fact was reproduced on Archer. When the OPTCLIM core establishes the number of runs it needs and creates interface directory, it also creates a job labeled post all runs here, and that will run the OPTCLIM software for the next iteration. So that's in a held job. It's held by an array of jobs which comprise tasks, one for each of the model runs, and it's these tasks that calculate the simulated observations. This array is also held, and the tasks in this array are released when the model has completed its run. So those are the concepts of OPTCLIM and the rationale for doing OPTCLIM and particle filtering. And now we'll look at what OPTCLIM on ARCHER2 looks like. So as I say, the software runs already on the university cluster Eddy. So our goal was to minimize the redevelopment of code, but to do the port to Archer, so replacing Redention with Slurm commands, and then adding support for these 3 exemplar models. The outcome, to give you the end of the story in the middle of it, is that the software is what we consider a beta release, so that some support is probably still needed, and offered on a best efforts basis by us from Edinburgh for new users of OPTCLIM with these models. Lots of people talk about going on journeys, and this was a journey of 3 phases because, and I'm illustrating that with my favorite sea kayak journey under an island off the Shetlands. And the first phase was to use MITgcm, and it has directories for source, for build, for run, and simple scripts. So it's the kind of setup that everyone who uses Archer is used to. In order to create the base model that is then cloned for each of the model runs required by OPTCLIM, all that has to happen is from an existing working model, add a command to the Slurm script, and that's the command which releases the simulated observation task, if you remember that. Cloning a model is very straightforward. It's just a copy of the run directory. Modifying parameters is simple. They're in name lists, and the current code using the Python module F90 NML achieves that for us. And then the run is a simple sbatch command run from the OPTCLIM framework. So now we'll have a quick look at CESM. Getting to know CESM takes a little bit more effort compared to MITgcm. CESM has a layer above Slurm. It has its own workflow that runs on Archer and has its own commands. But once you get to know them, once I got to know them, I realized it provided me with basically what I wanted. So that by modifying the workflow internal to the CESM, we could have the changes that did that releasing of a job for the simulated observations to be calculated. Cloning is very easy because there is a clone command. Modifying parameters is straightforward because you can write the parameter values you wish to change to a simple text file, and within the CESM workflow, it assimilates those new values and uses them in its name lists and what have you. And then to run the CESM, there's a CESM run command, and so that those commands and the combination of that and the workflow give us a layer above Slurm, but it's one which is quite straightforward to work with in our context. So from that sort of unfamiliarity, we move on to UKESM, which is a little more difficult, and it seemed to have some alternatives and obstacles we had to navigate, and more potential for getting into trouble. And UKESM uses systems called Rose and Silk, which I'll say a little more about in a moment, and runs these from a server Puma. So that to clone a model and to run it, you need the commands to execute on Puma. And the difficulty is that communication from OPTCLIM to Puma is a challenge. So that Puma is a server run by NCAS to help the UK community with the UKESM model. And this is what it looks like when you normally run UKESM on Archer. You connect to the Puma server, and there's a suite is defined by a set of text files which can be edited with an optional GUI, and these define a suite that is your model, that represents your model run. And then on Puma, you execute command Rose suite run, and that causes things to happen on Archer. It's very elegant and very powerful, but it's also a little daunting when you first meet it, because this is the kind of workflow which is quite typical, so that there's a number of jobs to do with the building. This one here is to do with the model running. Then there's some post-processing jobs here. And in this case, the data are optionally transferred to another machine for analysis. So this is what we needed to integrate with our OPTCLIM software. And the ideal way of doing that would have seemed to be to have basically the same OPTCLIM framework as before, but to move the clone and run commands so they execute on Puma, and that execution being triggered from the serial job, which is running OPTCLIM by an SSH command. So that would seem to be a nice way to go, but that nice way to go doesn't work at the moment, because Puma is the security arrangements between Puma and ARCHER2 mean that this SSH command can't happen. So that there's a problem in how OPTCLIM can communicate the fact that it wants a new clone of a suite to be made. communicating that request to Puma is a problem. And we decided to solve it by using a piece of software we had. Excuse me. It was called GeosMeta, which we'll come to in a moment. So that we have now got on Puma an extra coordinating suite that just causes the startup to happen, causes the OPTCLIM software to run. It makes a few specific parameter sets, and for each of them, they're written into one of these interface directories. Then what happens is that this coordinating suite goes into a polling loop, going around this loop, so that it runs a task which looks at the state of the runs as held in each of these directories. When OPTCLIM has defined a new one, it has a state of new, and this recognizes that a new model run is needed and sends a message via a service called GeosMeta that I'll explain in a moment. Well, it's a database in effect, web service database. So send writes to the database, and then over here in the coordinating suite, then have a job that looks in the database to see if any new requests have been received, and if so, then clone the rows suite by this is lovely. To clone a suite is just a copy of a suite. I was so happy to discover that's all that's needed, because in the work we did with the UM 4.5, that was tortuous. But so when a new suite is needed, the base suite gets copied, and then the rows suite for the model then executes. And that base suite includes tasks that run before the model is executed to copy pre-existing executables so that we don't have to do the build every time, and then to make modification to parameters, parameters, not params. Then the model runs, and the termination is recognized, and then the usual OPTCLIM array of tasks, or task in an array job runs for each model, and OPTCLIM runs again. OPTCLIM then defines new model sets it wants, new model parameter sets, and creates more of these directories with a particular status file, so that next time on Puma, the polling ticks around and it runs on Archer to look for these newly requested models. It can find them, send a request via GeosMeta, pick up that request, and then clone the next suite that's needed. So that's what we have running at the moment. And just a little bit more about GeosMeta, because this was a software that we've been developing in background mode for quite a while, really. The idea was that we recognized that we needed a way of holding metadata, and one that was accessible to all the computers that we used. And so we developed a web service called GeosMeta, which had some additional capabilities to do with being able to infer workflow if documents in GeosMeta described computations. But that had been sitting not heavily used, and still under background development as there was time to do it. But I realized that we could use that so that we can write to GeosMeta from Archer and read from Puma and hold status files in documents that can get updated. So we're using GeosMeta as a message passing layer. And the message contents are document type of suite request, and then the base suite name and the interface directory path, and and the message also holds the status, so that the one message written to GeosMeta only triggers one clone rather than repeated ones. The bad news is that while this works, it does mean that anyone running UKESM in OPTCLIM, it's only UKESM that this applies to, does need to be able to use GeosMeta. That's not that complicated, but it gives a dependency on us being able to run GeosMeta for the user, which is fine and part of what I'm willing to do. You know, the GeosMeta software has to be installed. The hope for news is that there will in time be a new Puma machine close to ARCHER2, and then the workflow that I was just describing can be made an awful lot simpler. So just to comment on that workflow, in these interface directories, we have flag files, you know, so that goes from new to requested, and then done. And then the changes, oh, excuse me, the coordinating suite, the new suite on Puma looks like this, so that R1 says when you first run the suite, just do this once, and it runs the, it starts the, runs OPTCLIM and up here in order to initiate the first set of models. And then it polls to ask this process to find the, to send requests for any new models that are needed, and then to get the requests, and then loops around this loop. So that's the way that gets expressed in rows. The base suite, then either side of running the model itself, we insert two tasks, a pre-run task and a post-run task. The pre-run task copying executables, and then using some code we wrote to amend parameters in the suite definition files. And then after the run, the post-run task runs that script that releases the array task for calculating the simulated observations, and updates the state of the model in the interface directories, so that that can be recognized by all the software components. An example of a real world trial. Here we had 4 parameters, and using an atmosphere only UM11 version of the UKESM, and you know, this wasn't meant to be a test of the efficacy of the methods, but just whether they worked, so that we didn't particularly try very hard to choose parameters or to choose the simulated observations. I think there were 22 observations and 4 parameters. I don't think it's usually that imbalanced in number, you know, but it shows that you know, we explored the parameter space using the DFO's algorithm, and ended up with just a tiny improvement. You know, but as I say, the goal of this was just to run with up to 19 or 20 runs and see what the algorithm did and make sure that the software worked. And we were content that that showed it did. So guidance for potential users of OPTCLIM. Whichever model you're running, you need to select parameters and your observations, and have code that will make simulated observations from your model of choice. you may need some support installing and configuring OPTCLIM for the first time. It's not packaged as elegantly as would be nice. And initial users with UKESM are likely to need some support. We ran with 3 different models, and in each of them we could add the pre-run and post-run tasks, but then we found that the model suites did vary in style, so that it's probably not that hard working out how to plug them in, but there's some difference also perfectly reasonably in what needs to be copied in order that we reuse pre-built executables, for example. But where support is definitely needed from us is in the need to use GeosMeta at the moment until new Puma comes along and we can have a much simpler workflow that integrates the rose silk of the UKESM with the OPTCLIM software. So I'd like to say a little bit more about the particle filtering. I alluded to why we do that in order to follow a storyline or a historical sequence of data. So I'll come on and say a little bit about that now. And, so in this case, well, maybe if we look at the top right, so that this shows that here an ensemble of models has been run, and the grey shading represents a range of data that's considered consistent with observations. So here we run a number of models with some kind of statistical perturbation distinguishing one from another. Choose the ones which are consistent with the historical data and run those ones on as a further ensemble, so that we begin with, say, in this case, an ensemble of 10 runs. 4 of them might be consistent with the observations, and perturb them to get a new set of 10 runs, and some of them are consistent with the observations. So we further perturb them and run them on, and so that you're dropping those runs which are inconsistent and continuing with your ensemble of 12 in this case 11 runs, which evolves according to what continues to match observation. And then when you reach the end of it, you can look back at the line. These green lines represent the path taken by an effective simulation that tracked the historical data. And I should have pointed out that the black line is the observation, and the grey line is the sort of range of acceptable variation from that. So that's what Andrew was seeking, well, Andrew was achieving with his particle filtering, and this ability to do a limited number of runs, and especially of short runs, in order to build quite a long timeline of an effective simulation. So that we begin by initiating an ensemble, run the models for a short period, and write out the model data, do an analysis that compares it against history, and then allows the selection of the particles or ensemble members that are deemed most fitting with history to be perturbed and restarted as a new ensemble. When we ran the particle filtering on EDDI, we actually used the OPTCLIM framework, and that was largely because, well, never mind why that was, but we did. When we came to run on EDDI, I realized that it was really quicker and simpler to let the code diverge from OPTCLIM, and so that our objectives were to minimize the code while learning from what we did with OPTCLIM and ARCHER2. Our focus was on making it work with UKESM, so that all of that, the use of GeosMeta was relevant here again. And so in running with particle filtering, the user needs to provide the historical data, the analysis that gives the goodness of fit of each model instance to the historical data, and determine how they wish to make perturbations before one of the particles is restarted. The status we've reached with this is that we've tested it with dummy filtering, and we're in the process of working on an example that is more real world. And the way the software looks is derived from OPTCLIM and different. It doesn't use the Slurm workflow as well, but uses run states held in the interface directories. So if we begin top left, we still have a coordinating suite that runs on Puma. There's a base suite, which is in an initial job cloned in order that an ensemble of jobs runs for the first time interval. There's an interface directory that holds the state of the runs. And then when each of the short runs is completed, that state changes. And then when they've all completed, then the filtering and the modification of dumps is done for the next time period. That is managed by this query status task, which itself is run from the polling on the coordinating task. So that every period this task executes, it checks the run states to see whether all runs are completed. If they are, then the filtering of the particles is done and the dumps are modified for the next set of runs. The status in these directories gets reset so that we don't repeat runs. And messages are sent to GeosMeta to request that runs complete. So it runs continue. So that the effect then is that this task picks up messages from GeosMeta. It extends the end run date and continues the runs on Archer. So in summary, the work we've been doing seeks to respond to models' uncertainties. We've ported OPTCLIM, which allows parameters to be tuned to observation. And we can do that on ARCHER2 with the 3 models, those based on MITgcm, on CESM and UKESM. OPTCLIM is in a sort of beta state where some support is likely to be needed, especially for UKESM if users adopt it. But we'll give that support on a best efforts basis. And we've developed the particle filtering with UKESM on ARCHER2 to follow the historical sort of storyline approach. We've used a different workflow using polling from a coordinated rows suite and holding state as in messages and in the interface directories that I showed you. And then we're in the process of doing a real world example, having tested the system with some dummy filtering, so I believe the software is working, but it would be good to have a more convincing proof to demonstrate the concepts of the particle filtering on ARCHER2. So that is about as much as I wanted to say. except to give great thanks for having the CSE grant. Thanks to Archer support, who, for example, when I realized that we couldn't queue enough serial jobs to be able to run the OPTCLIM workflow, made changes to the system to relax that constraint. And profuse thanks to MCAS, to Rosalind, David, and Grenville, who sort of really helped me a lot when there were questions that I was getting a little unclear about. And so thanks to them. And if any of what I've said they considered to be wrong, that's my fault and not theirs, I hasten to add. We have the project report and email addresses, for Simon, for Andrew, and for myself, if anyone wishes to explore trying this out. And thank you very much.
Okay, great. Thank you, Mike. Are there any questions? Feel free to either speak up or write them down in the chat.
Cool. Hi, Mike. Thanks for that. All right. I guess I have a clarification about UKESM, which I guess is just to make sure that I've got it right, that if we want to try this with UKESM, we really need to talk to you guys on all three of those possible topics, so installation and GeosMeta, and how we put the tasks into the Silk suites. Is that right?
Yes, the third one is probably much less the case, but I think that I would be happy to give support on the installation, and certainly until until a new Puma comes along, then the way I've managed to do it is through GeosMeta.
Yeah, okay. And then I'm afraid I was going to ask about UM4.5 and famous.
Oh, yes.
You very briefly alluded to that it was complicated, but you didn't talk about 4.5 at all otherwise. And I guess if I was going to use this, then famous would be the way I'd go rather than UKESM.
Okay, then what machine would be using it on?
So we're running it on Archer. So we've got the jobs on Puma with the UMUI, but we're running it on Archer.
Right.
So I don't know whether we'd have the same, but it's not in Rose Silk.
No, okay, so it's just standard UM 4.5. And the software that runs with 4.5 is still in there. I've not tried it on Archer, but we've been running it with Grid Engine on Eddy, and so it should be relatively straightforward to make that happen. But I'm just intrigued that you're running that you would be running it on Archer, given that Famous is such a relatively fast and light model.
So what we're really running on Archer, I suppose, is it's a version of the Famous atmosphere and land model coupled to an ice sheet model. So we run each instance on one node, but I suppose the atmosphere doesn't really take up very much of that. Nearly all of that's for the ice sheet model.
Okay.
But we are doing large sort of parameter tuning exercises with it. So this does sound like it might be a useful tool for that.
Yeah, well, it'd be fun to try, wouldn't it?
All right, I'll drop you a line about that as well then.
Oh, gladly. Yeah. No, the difficulty that I mentioned with 4.5 is that it's where we started with Eddy, but it's just not as simple cloning a 4.5 model as it is the others, in that you take copies, but then the names of jobs is scattered through various scripts, and so it's just things like needing to be meticulous, that you pick up the places where edits have to happen. So after you've done a copy, there's edits that are needed.
Yeah,
and that needs to be scripted. So we've been Simon's been running with 4.5 on Eddy a lot, and Andrew Schurer did his particle filtering with 4.5.
Yeah. Okay. Thanks then.
Pleasure. Are we done?
Okay, and I guess in that case, all that remains is to thank Mike again. So thank you for your talk, and then we'll have another one of these webinars next week. Thanks, everyone.
Thanks for your attention. Bye for now.